Welcome to the Sleepy Space Channel. This is your quiet corner of the evening, where the noise of the day fades and the universe takes a slower breath. Wherever you are, lying beneath soft lamplight, tucked into bed, or just letting the mind drift, I'm glad you found your way here. Tonight's calm journey explores one of the most beautiful puzzles in all of physics. Why does space bend? Before we begin, I'd love to know where in the world you're listening from. It's always fascinating to imagine this same stillness stretching across oceans and continents, connecting night skies everywhere. And if you're new here, a gentle reminder, a like and a subscribe really help this channel grow and reach more sleepy minds who enjoy drifting off to science. If you're already part of this little community, thank you. It means more than you might think. Don't forget to tap the notification bell so you won't miss the next quiet journey through the cosmos. I do hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll fall asleep a little wiser than before. So, let's begin softly with a question that has puzzled scientists for over 100 years. What if gravity isn't a force at all, but the shape of space itself? For as long as humans have watched the night sky, they've seen motion everywhere. The moon slides across its dark sea. The planets trace silent patterns, and the stars seem fixed, yet eternal. For most of history, this dance was explained by invisible pulls, gravity as a mysterious hand reaching across emptiness. It worked beautifully. But as we learned to measure time and motion more precisely, something strange began to show through the cracks. Every object, from a falling apple to a speeding planet, seemed to obey the same rule. They all fell alike, heavy or light, large or small. Each moved as if the universe itself were choreographing their steps. The question was why? Why would gravity treat everything equally? Why would light, which weighs nothing at all, bend around a star as if it too were following a path set out for it? In the early 1900s, a quiet revolution began. A young patent clerk named Albert Einstein suggested that gravity might not be a force pulling downward, but rather a change in the shape of space and time themselves. Matter, he said, tells space how to curve, and space tells matter how to move. It was a sentence so simple that it hid an entirely new vision of reality. This idea would transform how we understand orbit, starlight, and even time itself. It showed that the universe isn't a stage where things move. It's a living fabric that bends, stretches, and ripples. Tonight, we'll drift gently through that fabric, seeing how curvature creates everything we experience as gravity. We'll explore how falling can be a form of freedom, how clocks run at different rhythms, how light itself bends around stars, and how space can even ring like a bell when great masses collide. There's no rush, no math, and no pressure to remember anything. Just let the ideas unfold slowly, like constellations forming in the dark. By the end, the cosmos may feel a little less like a place of forces and more like a poem written in geometry. So settle in. The night is quiet, the universe patient, and somewhere beneath the curves of space, every star is part of the same graceful design. For centuries, gravity was understood as a kind of invisible handshake between objects, a steady, dependable pull that reached through the void. Sir Isaac Newton gave it a language that worked astonishingly well. With his laws, you could predict the path of an apple falling from a branch, or the arc of the moon around the Earth. The same equation that described a pebble's fall could chart the orbit of Jupiter. The universe, it seemed, had been tamed by mathematics and reason. In Newton's world, every object with mass tugged on every other object, no matter how far apart. The pull weakened with distance, but never vanished completely. It was a vision of harmony and universality, every atom whispering to every other atom across infinite space. For over 200 years, that idea reigned supreme. Engineers, sailors, and astronomers all built their confidence on it. If you knew the masses and distances, you could predict the future of planets themselves. But even in Newton's time, there was a small question lurking in the background. How exactly did this pulling happen? Newton himself admitted he didn't know. He called it action at a distance, a force that leapt invisibly across emptiness. It worked perfectly in the equations, but not in the imagination. Nothing seemed to travel between the Earth and the Moon. No rope, no wind, no particle carrying the message. Gravity, it seemed, acted faster than thought itself. Still, no one argued with success. The predictions fit reality so beautifully that most people simply accepted the mystery as part of nature's design. Then, as centuries passed and instruments improved, scientists began to notice something deeply curious. Every object, regardless of its weight or shape, fell in exactly the same way. A hammer and a feather would land together if the air were gone. A cannonball and a coin followed the same path. This was more than coincidence, it was a clue. Why would heavy and light things move identically if gravity were a pull proportional to mass? Shouldn't the larger object with more gravitational charge behave differently? The answer lay not in forces, but in geometry. The equality of free fall hinted that everything, no matter its mass, was following the same kind of path through space and time. It wasn't being yanked downward. It was simply moving naturally along the shape of reality itself. By the late 1800s, cracks were appearing in Newton's grand clockwork. Precise measurements of Mercury's orbit showed a tiny, persistent drift that Newton's equations couldn't quite explain. The difference was minute, just a few dozen arcsecans, but unmistakable dot. Something in the way gravity worked wasn't fully captured by the old rules. Meanwhile, new ideas about light and energy were reshaping physics. The stage was set for a revolution, and it would arrive not through a laboratory, but through thought. In the year 1905, a young patent clerk named Albert Einstein published a series of papers that would change the world. In one of them, he proposed that the laws of physics are the same for everyone, no matter how fast they're moving, and that the speed of light never changes. That simple statement led to special relativity, the first step in understanding time and space as part of the same fabric. Then, just a few years later, Einstein took a deeper look at gravity itself. He asked a question that no one else had dared to take seriously. What if gravity isn't a force at all? What if it's the shape of space and time bending around matter? Imagine a heavy object resting on a stretched rubber sheet. The sheet curves, and smaller objects rolling nearby naturally follow the curves. Not because they're pulled by a string, but because that's simply the easiest path available. Replace the sheet with space-time itself, and you have Einstein's insight in miniature. Matter tells space how to bend. Space tells matter how to move. Matter tells space how to bend, and space tells matter how to move. This was more than a mathematical trick. It solved the problems Newton had left behind. Gravity no longer needed to act instantly across distance. Its influence moved through space-time as ripples limited by the speed of light. Every planet, star, and grain of dust followed the same graceful path because all were tracing the same geometric, rule written into the universe. Free fall was no longer being pulled. It was motion along the natural lines of curved space-time. Einstein's vision was tested and tested again. It explained Mercury's wandering orbit perfectly. It predicted that light would bend when passing near the Sun, a forecast proven right during a solar eclipse in 1919. It predicted that time itself would slow near massive objects, a fact confirmed decades later with atomic clocks and satellites. Each success deepened the realization that gravity was not a mysterious force whispering across space. It was the quiet curvature of reality itself. And that curvature is subtle. The Earth bends space and time only slightly. You'd need a black hole to twist it enough to notice without instruments. But even here, every step, every falling leaf, every orbit of the moon follows the same law. Not because Earth pulls with invisible hands, but because space and time together form a landscape with valleys and hills, and everything moves according to that terrain. Einstein's equations, written in 1915, are famously dense, but their meaning is poetic. They say that the distribution of matter and energy determines the geometry of the universe. Where there's mass, space curves. Where there's energy, time stretches. A simple idea wrapped in deep mathematics. Gravity is not an external command. It's the universe responding to itself. The beauty of this picture lies in its gentleness. It doesn't replace Newton's gravity so much as complete it. Newton's theory still works beautifully for bridges, baseballs, and planets. Einstein's is simply more precise, stretching seamlessly from the smallest orbit to the curve of the cosmos itself. And all of it rests on a change in perspective, a decision to stop thinking of gravity as a tug and start seeing it as a pattern. You could say that gravity isn't magic. It's just very polite geometry. Matter quietly asks space-time to make room, and space-time obliges by bending ever so slightly. The result is the graceful motion of planets, the soft fall of an apple, and the subtle slowing of time. It's a universe that doesn't shout, but whispers in curves. Imagine standing in a small elevator somewhere in deep space, far from any stars, planets, or even the faint pull of a comet. You're floating, suspended in perfect stillness. If you let go of a key, it drifts beside you. There's no up, no down, no sense of weight, only the quiet hum of nothingness. This, Einstein realized, is what the true absence of gravity feels like. Not falling, not being pushed, simply existing in motionless freedom. Now imagine the same elevator, but this time it isn't floating in space. It's been cut loose, falling freely toward the surface of the Earth. The cables have snapped, but inside something curious happens. You let go of your key again, and once more it floats beside you. The floor doesn't press up on your feet. Your arms feel light. The sensation of weight disappears. The falling elevator and everything in it are all accelerating together at the same rate. So inside, it's as though gravity has been switched off. This is the heart of Einstein's great insight. Locally, falling freely in a gravitational field feels the same as drifting weightless through empty space. It's called the equivalence principle, and it sounds simple enough to write on a coffee mug, but it contains the seed of the entire theory of general relativity. To Einstein, this was not a mathematical curiosity. It was a clue to how the universe really works. Inside that falling elevator, the person, the key, and the feather are all moving together along the same curved paths that space and time dictate. None of them feel a force because, in a sense, there isn't one. Gravity in this picture isn't pushing or pulling. It's simply guiding motion along the natural geometry of space-time. What you feel as weight when you stand on solid ground isn't gravity itself, but resistance. The floor stops your body from following its natural free-falling path. Einstein's imagination lingered in that elevator for years. He pictured what would happen if it was sealed with no windows or instruments, giving away its location. Could you tell whether you were drifting in the still emptiness of space or falling freely toward a planet? You couldn't. Every experiment inside, tossing a ball, floating a feather, or even shining a beam of light, would behave identically. The laws of physics inside a freely falling frame were indistinguishable from those in the weightless void. That, to Einstein, was not coincidence. It was revelation. He called it the happiest thought of my life, because if gravity could vanish inside a falling room, then gravity must not be a true force at all, but a kind of illusion that arises when motion is prevented. When you fall freely, you're following the natural flow of space-time. When you stand still, it's the ground beneath you that exerts a force, not the Earth pulling on you. Think of an astronaut orbiting the Earth. From the ground, it looks like they're constantly falling. From their perspective, they're in endless free fall around the planet, never hitting the surface because the ground keeps curving away beneath them. Inside their capsule, they float. Not because gravity is gone, but because everything inside is falling together at the same speed. Gravity hasn't vanished. It's simply stopped opposing them. This idea also explains why being pressed into your seat during takeoff feels the opposite of floating. In that moment, you're being pushed upward by the rocket's thrust, while gravity is trying to let you fall. The push is what you feel as weight. It's resistance again, the denial of free fall. Once the engines cut and the spacecraft coasts freely, that resistance vanishes, and so does your weight. Einstein realized that this equality between acceleration and gravity, between falling and drifting, couldn't be a coincidence. It meant that gravity and acceleration were deeply connected. In a small enough region of space and time, you could always find a point of view where the laws of physics looked the same as they did in empty space. That's what locally flat means. The world might be curved overall, but in small neighborhoods, it's flat enough that you can pretend gravity doesn't exist. The difference appears only when you zoom out, step back far enough, and the illusion of flatness fades. Over large distances, free-falling paths that start parallel begin to converge or diverge. That's curvature, space-time bending under the influence of mass and energy. The beauty of Einstein's elevator is that it works as a bridge between the local and the global. Inside, you feel no gravity. Outside, the curvature of space-time shapes your motion. It's easy to mistake this as an abstract thought experiment, but it's something we experience constantly. Every time a skydiver leaps from a plane, their stomach's brief flutter isn't fear, it's geometry. They're in a small, temporary bubble of freedom, moving along the path Earth's curvature dictates. They feel weightless because, for those few seconds, they are. When the parachute opens and the straps tighten, the sensation of gravity returns. But what's really returned is the resistance of the air and the harness against their natural motion. The same principle explains why astronauts orbiting hundreds of kilometers above Earth are not outside gravity's reach. They're deep within it. Their continuous fall just never ends. The floor of their spacecraft no longer pushes up on them, so their bodies move freely along the paths that space-time prescribes. The result feels like floating, but it's really falling perfectly, endlessly, and peacefully. Einstein's elevator gave physics a new way to think about motion. Instead of seeing gravity as an invisible pull, he redefined it as the natural result of living in a curved universe. If you remove all resistance, flaws, cables, and rockets, you discover that everything moves freely and gracefully, following the geometry written by matter and energy. That's what freefall really means. Motion with nothing in the way. The quiet inside the falling cabin isn't just a metaphor for physics. It's a window into how the universe behaves when left alone. Every galaxy, star, and planet follows its own free-falling path through the fabric of spaced iamy. What we call gravity is simply the shape of those paths, written large across the cosmos. And somewhere in that silence, in that drifting elevator or the orbiting capsule, lies one of the most profound truths ever uncovered. The feeling of weight is not the presence of gravity, but the absence of freedom. If space were just a three-dimensional stage where things move and time was simply a ticking clock keeping score, the universe would be easy to picture. But the truth is far stranger and far more elegant. Space and time are not separate ingredients. They are threads of the same cloth. Pull on one and the other moves. Compress time and space stretches. Twist space and time bends with it. This woven entity is called space-time, and it's the stage, the script, and the motion all in one. To understand why, it helps to think about how we describe anything that happens. Every event, whether it's a supernova exploding, a raindrop falling, or you blinking your eyes, can be pinpointed only when we know both where and when it occurred. A location alone isn't enough. If you say the moon, that doesn't mean much unless you say when the moon was there, because it's constantly moving. Time is the fourth coordinate that makes every moment unique. Together, the trio of spatial dimensions and the single dimension of time give every event its complete address in the universe. That simple idea that where and when are inseparable was what led Einstein to unite space and time into a single structure. The concept sounds abstract, but you live it every day. When you move through space, you also move through time. If you stand perfectly still, you're traveling only through time, 1 second per second, steadily forward. When you start walking, a small part of that forward motion through time gets traded for motion through space. You don't notice the exchange because the speed of light is so vast that your share of it is minuscule. But the trade is there, quietly balancing every journey you take. Space-time has its own geometry, and it's different from the geometry you learned in school. In everyday geometry, the shortest path between 2 points is a straight line. In space-time, the shortest path between 2 events is the one that takes the least effort. Considering both distance and duration, that path is called a world line, a continuous thread showing where and when something exists. A resting object's world line points straight up through time. A moving object's world line tilts slightly, blending space and time together. The faster something moves, the steeper the tilt, until, for light itself, the line lies perfectly diagonal, the ultimate speed, the limit that no one can surpass. This is where the idea of intervals comes in. In ordinary life, distance and time are measured separately. You might say 2 towns are 30 kilometers apart, or that a trip takes half an hour. But in space-time, those numbers merge into one single quantity, the space-time interval. It's like combining space and time into a single distance that everyone agrees on, even if they disagree about the separate pieces. 2 observers, moving at different speeds, might not agree on how long something took or how far it was, but they'll always agree on the interval between events. That's the cosmic compromise. Reality reshuffles space and time depending on motion, but it keeps the combined truth the same. If this feels mind-bending, you're in good company. Early physicists wrestled with it too. They found comfort in something called the light cone, a way of visualizing what events can and cannot influence each other. Imagine a bright flash in space, a single spark like a camera bulb in the dark. Light spreads outward in every direction at the same speed, forming an ever-expanding sphere. Draw that expansion through time, and it looks like a cone rising upward. Everything inside that cone can, in principle, be reached by the light from the spark. Everything outside it is forever out of reach. That's nature's way of enforcing order, causality. Nothing can travel faster than light because nothing can move outside its cone. It's the universe's gentle rule for keeping time from contradicting itself. The light cone also shows why the past, present, and future are more than just words. Events inside the cone behind you are your past. They could have affected you. Events inside the cone ahead of you are your future. You could still affect them, but anything outside both cones is simply elsewhere, beyond influence. A galaxy 1 billion light years away could be shining right now, but its present light won't reach Earth for another 1 billion years. In a sense, its now and your now are disconnected. The universe keeps each patch of space-time honest to its own timeline. All of this might sound like abstract geometry, yet it describes something profoundly physical. Clocks, for example, don't all tick the same way. A clock on a fast-moving satellite runs slightly slower than one on Earth, not because it's broken, but because its path through space-time is different. Similarly, a clock near a massive planet ticks more slowly than one farther away, because mass curves space-time, changing how time itself flows. It's as though each object is walking on a flexible surface that bends and stretches depending on energy and mass. You can picture space-time as a vast fabric with time running vertically and space stretching horizontally. Every object, planets, people, light beams, is a thread weaving through it. Massive objects press down on the fabric, bending nearby threads toward them. Those bends are what we call gravity. If you could look at Earth's contribution to this tapestry, you'd see time flowing slightly slower near the surface than high above, and space ever so gently curved. This visualization isn't perfect. Space doesn't literally sag like a trampoline, but it captures the idea that geometry replaces force, where Newton imagined invisible strings pulling on distant objects. Einstein replaced those strings with curves and slopes in the fabric of space-time. The Earth moves around the Sun not because it's pulled, but because it's following the straightest possible path through a curved geometry. The Sun's mass tells space-time how to bend, and space-time tells Earth how to move. The beauty of this unification is that it removes the need for mysterious connections across emptiness. Nothing reaches out instantly. Everything communicates through the structure of space-time itself. Light acts as the ultimate referee, setting the fastest possible pace for cause and effect. No matter who you are or how you move, the speed of light stays the same, and the shape of your personal light cone tells you what's possible. Space-time isn't an invisible background, it's an active participant. When massive stars collapse or galaxies collide, the fabric doesn't just sit there, it ripples. When black holes twist, space-time swirls. When light travels, it rides the fabric itself. Every second of every life unfolds along a tiny piece of this cosmic weave. Einstein's merging of space and time gave the universe continuity. It's no longer a stage where events happen. It's the script and the stage combined, a dynamic fabric in which matter and motion are inseparable. Time doesn't flow separately from space. It flows through it, shaped by gravity and motion. That's why we can't fully speak of space or time alone. They're threads of one vast tapestry. So the next time you look up at the stars, imagine them not scattered across emptiness, but stitched into an enormous fabric. Every thread vibrating gently, every moment connected by geometry. Space and time are partners in the same cosmic dance, turning every falling apple and every drifting galaxy into part of one continuous story, a story written quite literally in curves. When we think of a straight line, we usually imagine something simple: a ruler's edge, a laser beam, the shortest path from one point to another. But in a curved universe, straight becomes a matter of perspective. On a sphere, for instance, the shortest path between two cities isn't a flat line on a map, but a curve known as a great circle. Airplanes follow these routes every day, arcing gently over the poles because that's the most efficient path. Even though it looks curved on a flat chart, this idea, what it means to be straight when the surface itself is curved, is at the heart of understanding gravity and motion in Einstein's universe. In space-time, the equivalent of a straight line is called a geodesic. It's the path that takes the least effort, the most natural route an object can follow through the four-dimensional fabric of space and time. A planet orbiting a star, a satellite circling the Earth, even a beam of light passing near a massive object. All of them follow geodesic. There's no pushing, no pulling, no mysterious force tugging them off course. They simply glide along the curved geometry that matter and energy create. You can think of a geodesic as nature's path of least resistance. A marble rolling freely across a smooth surface doesn't choose where to go. It follows whatever contour the surface gives it. The same happens in space-time when you're falling freely with no engine, no rocket, and no floor pushing against you. You're following a geodesic. That's why astronauts floating inside the International Space Station feel weightless. They haven't escaped Earth's gravity. They're simply moving along the natural curve of space-time around Earth, falling perfectly and perpetually. If the Earth weren't there, that path would be a simple straight line through space. But Earth's mass gently bends space-time, turning that straight line into a graceful arc. To the astronauts, the world feels still and serene. To an observer on the ground, they're in constant motion, looping endlessly around the planet. Two perspectives, one reality, a straight line in curved space-time. This concept may sound abstract, but it's deeply intuitive once you let go of the idea that space must be flat. Picture yourself walking across the surface of a globe. You start at the equator and head north along a line of longitude, trying your best to walk straight. To you, your direction never changes, yet from above, your path curves toward the pole. If two people start at the equator side by side, walking north along neighboring longitudes, they begin close together but eventually meet at the pole. Neither of them ever turned, but their paths converged. That subtle drift between nearby straight paths is the essence of curvature. In Einstein's language, this is called geodesic deviation. How we detect the presence of curvature by watching how two free-falling objects that start parallel begin to move together or apart over time. In a flat world, they'd stay perfectly aligned forever. In a curved one, Even a tiny separation tells us how space-time bends. You don't need fancy equations to imagine it. Just think of two boats drifting on an ocean. At first, the water seems flat and calm, but as they travel, currents pull one slightly faster, the other slower. Their paths, which began parallel, now diverge. Neither boat did anything special. The shape of the ocean did. The same idea plays out across the universe. Two asteroids passing near Jupiter will have their trajectories ever so slightly altered, curving differently depending on their starting positions. Their motion reveals the planet's mass, not because it pulls on them directly, but because it shapes the geometry of the space they move through. The geodesics they follow gently twist like threads in a woven cloth, bending around a knot. Even light obeys this rule. When a beam of starlight passes close to the sun, it bends, not because the sun reaches out to grab it, but because the geometry of space-time near the sun is curved. Light always follows the straightest possible route, but in a curved universe, even the straightest path can look like a curve from afar. The stars that astronomers see near, the sun's edge during an eclipse are slightly displaced, their light bent along those It's nature's own lensing written into the structure of reality. One of the most elegant aspects of geodesics is how democratic they are. Massive or massless, large or small, everything follows them. A planet, a photon, a grain of dust all move along paths determined solely by the geometry of space-time, not by their size or composition. That's why on the moon, a hammer and a feather fall side by side. They're not obeying a command from gravity. They're following the same natural route through the same curved geometry. Understanding geodesics also helps explain why astronauts and satellites appear to float even while surrounded by gravity. The International Space Station, for example, orbits about 400 kilometers above the Earth, moving at over 27,000 kilometers per hour. It's constantly falling toward the planet, but the ground beneath keeps curving away at just the right rate. Inside, everything falls together, the crew, the air, the equipment, so no one feels a thing. They're traveling along a shared geodesic guided by Earth's curvature, free from any sensation of weight. You can imagine the same principle on a smaller scale. Toss a set of keys upward and watch them arc back down. To you, it looks like a neat parabola, a temporary flight and a fall. To space-time, it's a continuous curve along a geodesic straight when seen in the right. Four-dimensional light, the keys don't switch direction halfway through. They simply trace the path the geometry dictates. What makes geodesics so powerful is that they describe motion without invoking forces. The word gravity becomes shorthand for the shape of space-time. When we say an apple falls to the ground, we are really saying it's following a geodesic that leads to the center of the Earth's curved geometry. When we say the moon orbits the Earth, we're describing another geodesic, one that happens to close back on itself, forming a stable loop. Gravity, in this view, is geometry experienced in motion. It's humbling to realize that every movement we make, every step, every leap, every orbit is a thread in this vast geometric web. The shape of the cosmos determines the story of motion, and we, without even trying, follow its lines. The next time you see a leaf drifting on a stream, notice how it glides effortlessly along the current, adjusting to every bend in the river without thought or struggle. That leaf is following a geodesic, tracing the natural flow of the water beneath it. In the same way, planets and light, and even you, are all drifting along the currents of space-time. So when someone says that objects move in straight lines, they're not wrong, just incomplete. Straightness depends on the surface beneath. In a flat universe, lines stay apart forever. In a curved one, they meet, cross, and diverge, shaping the patterns of orbits, tides, and galaxies. The Earth, the stars, and the light between them all trace these quiet, graceful lines. The universe may look chaotic, but at its core, it's guided by the simplest rule imaginable. Everything moves straight ahead. And it's the shape of space itself that decides what straight really means. Time has a rhythm, but it isn't universal. It doesn't march forward at the same steady pace everywhere in the cosmos. It bends, stretches, and slows depending on where you are and how much gravity you're surrounded by. This isn't poetic exaggeration. It's measurable, precise, and deeply woven into the nature of space-time. The stronger gravity is, the slower time flows. Mass bends not only space, but the flow of moments themselves. It begins with energy. According to Einstein, energy and mass are two sides of the same coin. Anything that carries energy, be it a planet, a beam of light, or a handful of starlit dust, contributes to gravity. Where energy pools, space-time curves, and where space-time curves, time itself ticks more slowly. This means that near any massive object, from a planet to a black hole, clocks run ever so slightly behind those farther away. The effect is tiny on Earth, but across the universe, it becomes one of the grand rhythms that shape reality. You can test this without ever leaving home. Imagine two identical clocks, one resting at sea level, the other on a mountaintop. Both tick in perfect unison when synchronized. But as the days pass, the mountain clock pulls ahead, gaining a few nanoseconds every 24 hours. The difference is absurdly small, yet undeniably real. Time runs a little faster up there because gravity is weaker. The higher clock feels less of Earth's curvature tugging at it. Down by the sea, where Earth's gravity is slightly stronger, time slows by the tiniest fraction. The difference would never matter to a wristwatch, but to a satellite, it's everything. Your smartwatch, if it could talk, might be quietly proud of this fact. If you climbed a tall hill, it could brag that it's running ahead of every clock in the valley by a few trillionths of a second. The higher you go, the less gravity holds you, and the faster your seconds stretch out at the summit. You're aging fractionally faster than the people standing at the beach. Not enough to earn any wisdom points, but measurable all the same. The idea that gravity can slow time isn't just theory. It's been confirmed over and over again. In the late 1950s, physicists Robert Pound and Glenn Rebka ran a beautifully simple experiment in a Harvard University tower. They placed a source of gamma rays at the top and a detector at the bottom. Because the rays had to fall through Earth's gravitational field, their light was slightly blue. Its frequency increased, meaning time at the bottom ticked just a hair slower. The difference was minute, but the instruments caught it perfectly. Einstein's prediction was right again. Decades later, atomic clocks made these tests even sharper. In one experiment, two of the world's most precise clocks were synchronized. One was left on the ground, the other was flown in a jet for a few hours and then brought back. When compared, the airborne clock had ticked slightly faster, just as relativity predicted. Similar results were found using rockets and satellites. No matter how many times the tests were run, the message was the same: time is elastic, and gravity gently stretches it. It's easy to take time for granted because our senses can't detect its shifts. You don't feel the seconds slowing when you step into a valley, and your heart doesn't beat faster on a mountain. The effect only shows up when we measure with extraordinary precision. Atomic clocks counting vibrations of cesium atoms so steadily that they could keep perfect time for millions of years without losing a second. Yet, even with that stability, gravity wins. A height difference of just a few tenths of centimeters can now be detected in time dilation. That's how sensitive our instruments have become. Modern clocks can literally feel the curvature of the Earth. But what happens when you push this idea to extremes? Near massive stars or dense objects like neutron stars, the slowdown of time becomes staggering. A neutron star packs more mass than our Sun into a sphere barely 20 kilometers wide. Its gravity is so intense that time near its surface slows to a crawl compared with time farther away. If you could hover safely above it, which you can't, but imagine seconds for you would pass, while minutes or even hours might pass for someone watching from afar. The star doesn't just warp space, it needs time itself into new shapes. And then, of course, there are black holes, the champions of gravitational time distortion. Near a black hole's event horizon, time slows so dramatically that, from the viewpoint of a distant observer, it appears to stop altogether. Light climbing out of that region stretches endlessly, losing energy until it fades to invisibility. To an outside observer, nothing ever truly falls in. It just slows, redder and redder, forever on the brink. From the perspective of the falling object, however, everything feels perfectly normal. It crosses the horizon in finite time, unaware that, from the outside universe's point of view, it has practically frozen in place. Two perspectives, both correct, depending on which part of space-time you call home. This isn't science fiction. It's the architecture of reality. Even our technology depends on it. The global positioning system, those small satellites orbiting high above, must constantly account for both their speed and their height. Moving quickly slows their clocks slightly. Being farther from Earth's gravity speeds them up. The two effects nearly cancel, but not quite. Engineers must correct for a difference of about 38 microseconds. That may not sound like much, but without the correction, GPS positions would drift by several kilometers in less than 24 hours. Your phone's map would show you walking through walls or driving across rivers. These same principles ripple through the universe. In the cores of galaxies, where supermassive black holes sit like heavy anchors, time moves at a different tempo than it does between the stars. Even on Earth, time isn't uniform. It runs faster in skyscrapers than in subways. Every clock, from your wrist to the heart of the Milky Way, ticks according to the gravity it feels. We live in a universe where every place has its own tempo, its own local rhythm. Einstein's equations didn't just redefine gravity, they redefined time itself. Before him, time was the great constant, the same for everyone, everywhere. After him, it became dynamic, personal, and curved. The deeper you are in a gravitational field, the more space-time is stretched, and the slower your seconds unfold. The stronger the curvature, the heavier the hand that holds the clock. There's something oddly comforting about that. Time isn't an unyielding metronome. It's supple, responsive, and alive to its surroundings. It listens to mass, to energy, to motion, and quietly adjusts. The universe doesn't keep a single time. It lets every corner breathe at its own pace. So yes, your smartwatch really would get a little smug with altitude. It's not just higher, it's ahead. Ever so slightly, somewhere deep in that tiny circuit, it's ticking in proud defiance of gravity's gentle hold. And while you won't feel the difference, those nanoseconds matter to the satellites above, to the signals that guide your path, and to the scientists measuring the pulse of the cosmos. Time stretches softly around you every second of every day. A quiet reminder that even the most constant thing in the universe still knows how to bend. Light is tireless but not invincible. When it climbs away from a massive object, it pays a price for its escape. It loses a little energy, stretches its wavelength, and its color drifts ever so slightly toward the red end of the spectrum. This gentle stretching of light is called gravitational redshift, and it's one of the quiet signatures of curved spacetime. To the universe, it's a simple rule. Where gravity is strong, light must work harder to leave, and even light can grow weary. Imagine a photon born near the surface of a star. It begins its journey upward, carrying energy in the form of a short, tight wavelength, perhaps blue or violet, as it rises. The star's gravity tugs on it, not in the way it would tug on a falling apple, but through the geometry of space-time itself. Climbing away from the curve, the photon must spend part of its energy just escaping. But light can't slow down. It always travels at the same cosmic speed limit. The only way to spend energy without changing speed is to change color. Its wavelength stretches, its frequency lowers, and its hue slides toward red. By the time it reaches the empty void beyond the star, it's the same light, just slightly older, slightly longer, slightly tired. This is different from the redshift caused by motion or expansion. In a Doppler redshift, light stretches because the source is moving away, much like the drop in pitch when a train whistle passes by. The waves are literally stretched out in transit because the emitter is retreating. A cosmological redshift, on the other hand, happens because the universe itself is expanding. Space grows between galaxies, carrying the light with it like paint stretching across a balloon. Gravitational redshift is subtler. The source may stand perfectly still, but space-time itself is curved in such a way that climbing away from mass is like hiking uphill through molasses. It's not about movement through space, but movement through gravity's gradient. This effect is everywhere, even if we rarely notice it. Light leaving the surface of Earth, for instance, is redshifted by an almost imperceptible amount, just a few parts in a billion. But in the intense gravity of a white dwarf or a neutron star, the difference becomes enormous. The dense mass bends space-time so sharply that light leaving its surface can lose a noticeable chunk of energy. Astronomers can measure this loss and use it as a way to weigh stars without ever touching them. The stronger the redshift, the deeper the gravitational well from which the light has climbed. The first clear terrestrial test of this effect came in the late 1950s. At Harvard University, in a small 22-meter tower that has since become one of physics' quiet monuments. Robert Pound and Glenn Rebke devised an ingenious way to test Einstein's prediction here on Earth. They used gamma rays, tiny packets of extremely energetic light, and aimed them down the length of the tower dot according to relativity. As the light fell, it should gain energy, becoming ever so slightly bluer, while light traveling upward should lose energy, becoming redder. The difference, even over just a few floors, was so small it bordered on impossible to detect. But with exquisite precision, using what's known as the Max-Bauer effect, they managed to measure it. The result matched Einstein's calculations almost perfectly. It's worth pausing to appreciate the subtlety of that experiment. The tower wasn't particularly tall. and the gamma rays changed frequency by an amount smaller than 1 part in 100 trillion. Yet the universe played along faithfully. Gravity, it seemed, really did stretch light, just as Einstein had promised. This wasn't theory anymore. It was observation. The same effect that bends time and curves space could be measured in a college physics, building with patient hands and clever thinking. Once scientists knew how to look, they began to find gravitational redshift in the heavens. Light from the surface of our sun shows it. Light from compact white dwarfs shows it even more strongly. By measuring just how much the light's frequency shifts, astronomers can calculate how much gravity a star exerts and therefore estimate its mass and size. It's one of the simplest but most elegant tools for probing the invisible architecture of the universe. In galaxies farther away, gravitational redshift also plays a small but telling role. The centers of massive galaxies, where dark matter and supermassive black holes dwell. Warp spacetime so severely that even the glow of stars around them leaves at a lower pitch of light. When astronomers compare the light from the outer parts of a galaxy to the light from its core, they can see the fingerprints of this stretching. It's not much, but it's enough to reveal how deeply the galaxy curves the space around it. To visualize it, imagine light as a small, determined climber on an endless hill of gravity. At the base, near a massive object, the climber is bright and full of energy, every step packed with momentum as it ascends. Each step costs effort. There's no wind, no friction, just the invisible slope of space-time itself. By the time it reaches the summit, it's panting slightly, its steps longer, its rhythm slower. It hasn't lost heart, but it has lost energy, stretched thin by the climb. That is the gravitational redshift in motion, a photon catching its breath on the long way out of a star's embrace. This redshift also explains something beautifully simple. Light doesn't fall the same way that matter does, but it still feels gravity's influence. A stone thrown upwards slows, stops, and falls back because gravity pulls on its mass. Light, with no mass, never stops or falls back, but its wavelength still stretches as it escapes. Gravity shapes both energy and geometry. Neither gets a free pass. You can even see the same principle working in reverse. When light falls toward a massive body, it doesn't slow down, it can't, but its frequency increases. The color shifts toward blue as energy is added. That's called gravitational blue. It's the mirror image of the redshift, showing that gravity doesn't just stretch light. It can squeeze it too, depending on the direction of travel in the wider cosmos. Redshift is the language of distance, motion, and gravity all at once. Astronomers have to separate the causes carefully. When they see light stretched from distant galaxies, they ask, is it the expansion of the universe, or the gravity of the source, or its motion through space? The answer can reveal the mass of a star, the presence of a black hole, or even the rate of cosmic growth itself. Every subtle tint of red tells a story. The gravitational redshift is one of those triumphs of science that feels almost humble. It doesn't make headlines like black holes or supernovas, but it's the quiet proof that gravity and light speak the same language. Every photon that leaves a planet, a star, or a galaxy must pay its toll in energy to escape. Most of the time, the fee is tiny, barely perceptible, but in the deep wells of massive objects, the cost becomes enormous, and light itself grows weary on the climb. So the next time you see the soft glow of a sunrise, remember that those golden rays are a little redder than when they began their journey. They've climbed out of Earth's slight gravitational pull. stretched just a fraction on their way to your eyes. It's a delicate reminder that even light, for all its speed and brilliance, is still part of this curved and patient universe. Sometimes even photons need to stop and catch their breath. Light, for all its speed and brilliance, seems like it should be immune to gravity. After all, photons have no mass, nothing to pull on, nothing to weigh down. Yet the universe has a quiet way of humbling even its swiftest traveler. When light passes near something massive, like a star or a galaxy, its path bends. It doesn't bend because the light is tugged or slowed, but because the space it moves through is curved. The photon is still following the straightest possible route. It's just that, in curved spacetime, straight doesn't always look straight to us. To grasp this, imagine a marble rolling across a smooth table. On a flat surface, it moves in a perfect line. But if the table sags slightly in the middle, the marble's path will curve as it follows the slope. The marble hasn't changed its mind or felt a sideways push. It's still taking the easiest route available. Space works in much the same way. When light glides past a massive object, it's not being pulled sideways, it's tracing the geometry of the curved spacetime around it. Einstein predicted this in 1915 when he first completed his general theory of relativity. He calculated that light passing near the sun should bend by about 1 3/4 arcseconds, a barely noticeable angle, but one that could, in principle, be measured. If he was right, the positions of stars near the sun's edge during a total solar eclipse would appear slightly shifted from where they'd normally be. It was a bold claim, one that needed the rare coincidence of a clear sky, a perfect eclipse, and patient observers on the far side of the world. That chance arrived 4 years later. In May of 1919, 2 expeditions set out under the British astronomer Arthur Eddington to capture the moment. One to the island of Principe off the west coast of Africa, and another to Sobral in Brazil. As the moon slid across the sun, blocking its glare, the stars near the darkened disk came into view. Using long exposure photographic plates, Eddington and his colleagues compared the apparent positions of those stars during the eclipse with their usual positions in the night sky. When the results were developed, the stars near the sun's rim had shifted by exactly the amount Einstein had predicted. It was a quiet revolution captured in silver emulsion. The bending of starlight was the first experimental confirmation that gravity could curve space and time. Overnight, Einstein became a household name. Newspapers printed his equations as if they were poetry. Headlines read, "Lights all askew in the heavens." The universe, it seemed, had rewritten its rules. What had once been an invisible tug was now revealed as a graceful bending of geometry itself. The story didn't end there. Over the following decades, astronomers found that this bending of light wasn't confined to stars near the sun. It happens everywhere, all the time. On every scale, when light from distant galaxies passes through the curved spacetime of clusters of galaxies in the foreground, the images we see from Earth can be stretched, magnified, or even multiplied. Sometimes the alignment is so perfect that the light forms a glowing ring around the lensing galaxy, called an Einstein ring. Other times, we see delicate arcs and mirrored smears of light, the cosmic fingerprints of spacetime curvature. This phenomenon, known as gravitational lensing, is now one of the most powerful tools in modern astronomy. It lets us map the invisible dark matter, which neither emits nor absorbs light, but still bends it through gravity. By studying how background galaxies are distorted, scientists can trace where mass hides, painting detailed portraits of cosmic structure. Even the most distant galaxies, whose light has traveled for billions of years, can be revealed through this natural magnifying glass. The universe, in a sense, provides its own telescope. It's easy to imagine that gravity somehow pulls on the light as it passes. But that's not quite what's happening. Gravity doesn't reach out and grab the photon. It's the space itself that's warped. The photon isn't changing its behavior. It's just doing what it always does, traveling in a straight line through whatever space-time gives it. If space-time bends, the path bends too. The distinction might sound subtle, but it's everything. It's the difference between a force acting on light and light simply obeying geometry. A good way to picture it is to imagine a beam of light as a long ribbon stretched across space. When space-time curves near a massive object, the ribbon follows the bend like a silk scarf drifting over a round globe. The light doesn't fall into the curve. It simply moves across it, smooth and graceful, obeying the topography of the universe. What we see from a distance is a deflection, a change in direction, but to the light itself, nothing unusual has happened. It's still traveling straight ahead. This subtlety becomes clear when comparing the deflection of light to the motion of matter. A comet passing near the sun curves because it's both pulled by gravity and moving through curved space. A photon, having no mass, only feels the geometry. It doesn't respond to gravity as a force. Yet both end up curving in a similar way because their motion is shaped by the same warped space-time. Matter feels curvature as gravity. Light reveals curvature through its path. The amount of bending depends on how much mass is present and how close the light passes. The sun's deflection is tiny, but near more massive objects like black holes or galaxy clusters, the effect can be dramatic. In some cases, light can even orbit a black hole several times before escaping, tracing loops in the intense curvature near the event horizon. In those moments, light becomes a dancer on the edge of geometry, balancing perfectly between freedom and capture. Gravitational lensing isn't just a cosmic curiosity, it's a window into deep time. The light that reaches us today from distant galaxies has been bent, delayed, and stretched by the matter it's passed along the way. By studying those distortions, astronomers can measure how fast the universe is expanding and even test whether Einstein's theory still holds true on the largest scales. So far, every test, every curve and arc in the sky agrees with his predictions. If you could stand in the vacuum near the sun and watch a beam of starlight pass by, you wouldn't see it jerk or twist abruptly. It would glide smooth and unbroken, curving almost imperceptibly as it brushed past the glowing surface before continuing into the dark. It would be like an arrow loosed from a bow, flying true yet following the natural curve of the bowstring that launched it. The path would look bent to a distant observer, but to the light itself, the journey would still feel perfectly straight. That's the quiet beauty of Einstein's universe. Even light, the fastest thing there is, doesn't escape the influence of shape. It moves with the grace of a traveler, tracing the contours of invisible hills, guided not by force, but by geometry. And somewhere in that faint arc of starlight, bending silently across the void, the story of gravity is written in light. In the quiet rhythm of the cosmos, every planet, moon, and asteroid is falling. The Earth is falling around the sun, the moon is falling around the Earth, and even the sun itself is falling slowly around the center of our galaxy. Yet none of these worlds crash into one another. They fall perfectly, perpetually, tracing elegant loops through the fabric of space-time. Each orbit is a dance of geometry, not of force, a straight line drawn across a curved map. When Newton looked at the planets, he saw a grand balance of pushes and pulls. The sun's gravity tugged on each planet, pulling it inward, while the planet's motion tried to carry it forward in a straight line. The result was a stable orbit, an endless compromise between falling and flying. For centuries, this picture explained the heavens beautifully. But Einstein's view transformed that tug-of-war into something more serene. In his universe, the planets aren't being pulled at all. They're free-falling along the straightest possible paths through the curved space-time. Around the sun, it's an elegant illusion. From our human viewpoint, we see circular and elliptical orbits, as though the planets are whirling in invisible harnesses. In reality, they're doing nothing but following geometry. They're like pebbles rolling along a gently curved bowl. The shape of the bowl decides the motion, not any hidden string or pull. In space, that bowl is the sun's curved space-time, deep in the middle, shallower toward the edges. Each planet glides along its own contour line, always falling but never colliding. This realization changes how we imagine motion itself. There's no need for a constant force to keep the planets in orbit. Their momentum carries them forward, while the geometry of space-time continuously redirects them, bending their straight paths into circles or ellipses. They're always moving straight ahead. It's the space they move through that curves beneath them. That's why gravity is sometimes described not as something that pulls, but as something that tells. Matter tells space how to curve. Space tells matter how to move. The conversation between the two is continuous and unending. It's a dialogue written in orbits, tides, and the passage of time before us on Earth. This curvature is subtle but omnipresent. Every apple that falls, every ocean tide that swells, every satellite that stays aloft is answering to the same geometry. You can even see traces of relativity in the details of Mercury's orbit. For centuries, astronomers had puzzled over a tiny mismatch between Newton's predictions and the planet's actual motion. Mercury's path around the Sun wasn't perfectly steady. Its closest approach shifted slightly with each orbit. A slow, graceful twist called the precession of the Perihelion. No matter how precisely Newton's laws were applied, the numbers wouldn't quite fit. It was as if Mercury were responding to a whisper the equations couldn't hear. When Einstein applied his new theory of curved spacetime to the problem, the missing whisper was found. The curvature near the Sun, tiny but stronger than anywhere else in the solar system, was enough to explain Mercury's wandering path. The correction wasn't guessed or forced. It fell naturally out of the equations, a quiet confirmation that the geometry of spacetime was real and measurable. Einstein's theory didn't just match Mercury's motion. It predicted the exact amount of precession, 43 arcseconds per century. The same figure that had puzzled observers for decades. For the first time, the dance of the planets made perfect sense. Not as a mechanical system of forces, but as the elegant unfolding of curved geometry. Every orbit, from Mercury's quick loop around the Sun to the slow drift of Pluto at the edge of darkness, is a trace of the same universal law. Even light, as it skims past the Sun or bends around a galaxy, follows the same principle. It moves straight ahead through a curved world. On human scales, the curvature of space-time is far too gentle to notice. A dropped pen falls because the floor stops it. Not because space feels obviously bent, but expand your vision to the scale of planets and stars, and the bends become visible in motion. Step wider still to galaxies and clusters, and space-time itself begins to ripple. Those ripples are gravitational waves, vibrations, in the fabric of space-time that carry energy across the cosmos. Einstein predicted their existence in 1916. Just a year after publishing General Relativity, he realized that if massive objects, like stars or black holes, move suddenly, colliding, orbiting, or merging, they should send out waves of curvature. Much like ripples spreading on a pond, these waves travel at the speed of light, stretching and squeezing space as they pass. But for a century, they remained undetected. The effect was so faint that even the most violent cosmic events would shift distances on Earth by less than the width of an atomic nucleus. It wasn't until 2015 that humanity finally heard their whisper. Two enormous detectors, one in Louisiana and another in Washington state, together known as LIGO, picked up a faint, rhythmic signal. It was the final echo of two black holes spiraling into each other over 1 billion light-years away. For a fraction of a second, their collision released more energy than all the stars in the observable universe combined. Yet by the time those waves reached us, they were barely noticeable, a change in length smaller than a proton. Still, the detectors felt it. The signal matched Einstein's predictions exactly. The waveform showed the black holes circling faster and faster, then merging in a burst of gravitational energy before fading into silence. It was the sound of space-time ringing like a bell. That discovery opened a new era of astronomy. For the first time, we weren't just seeing the universe through light. We were listening to it through gravity itself. Every ripple tells a story. The merger of neutron stars, the spin of black holes, the death of massive suns. These waves pass through everything, barely slowed or absorbed. They carry with them the shape of their origins, like music resonating through the bones of reality. In the years since LIGO's first detection, more observatories have joined the chorus. Virgo in Italy, Kagra in Japan, and soon, detectors in space that will listen to lower, deeper frequencies. Together, they will map the gravitational symphony of the universe, revealing collisions, mergers, and movements invisible to any telescope. Einstein himself doubted these waves would ever be detected. He thought they'd be too faint, too delicate. Yet the universe proved generous, and our technology patient enough to hear them. Gravitational waves confirm, in the most direct way possible, that space-time is not just a concept or a coordinate grid. It's a physical, flexible fabric that can ripple, vibrate, and carry energy. The cosmos is not silent. It hums. Every orbit, every fall, every collision adds its note to the grand harmony. Some waves ring for billions of years, others for seconds. But together they weave a melody older than light itself. If you close your eyes and imagine the universe as a vast sea, then gravity is the shape of its waves, and space-time is the water they move through. We float upon it, ride its swells, and never once notice the movement beneath, the planet's orbits. The starlight's bending, the slow ticking of clocks, all are echoes of that silent sea in motion. Every so often, that sea stirs with something immense. Two black holes spiral together, their orbits tightening as they shed energy through gravitational waves. With each lap, they move faster, their rhythm quickening like a heartbeat rising to a crescendo. And then, at last, they merge to horizons, becoming one, the surrounding space-time trembling with the release. For a fleeting instant, the universe itself vibrates. Those ripples rush outward in every direction, carrying the memory of the collision across billions of light years. By the time they reach us, the waves are unimaginably faint, but still perfectly in tune with the laws that sent them. It's a reminder that even the grandest events in the cosmos eventually fade into silence. Yet their echoes persist, recorded in the stretching and squeezing of space-time, waiting patiently for us to listen. Every detection of gravitational waves is a kind of cosmic archaeology, not of rocks or fossils, but of geometry itself. Each wave is a fossil of motion, a preserved pattern of how the universe once flexed and swayed. By studying these faint signals, we can reconstruct events we'll never see with light: black holes that swallow one another, neutron stars that collide and forge the elements that become planets and life. When two neutron stars merge, their combined mass briefly glows in every wavelength: gamma rays, X-rays, visible light, and radio, and also sends out gravitational waves that arrive first, announcing the event before any telescope catches the flash. This connection between light and gravity waves has opened a new window, letting us watch the universe not just with our eyes, but with its heartbeat. You can think of space-time as both the canvas and the drum of existence. It records every stroke, every rhythm, every echo of energy. When a black hole collision rings through that drum, it's the universe's way of keeping time. For all its vastness, it still has a pulse. These ripples also help us measure the expansion of the cosmos itself. By timing how gravitational waves stretch and fade as they travel, scientists can calculate how far they've come, giving new clues to the size and age of the universe. It's as though space-time carries its own built-in rulers and clocks, woven into the texture of the waves. The same waves that once escaped the fury of collapsing stars now glide through your body, your room, the entire Earth, right this moment. They pass unnoticed, harmless, stretching and relaxing space by amounts smaller than an atom, yet never stopping. We live in a sea of motion that never rests. If the cosmos is an ocean, then we are waves within waves, patterns inside patterns. The elegance of Einstein's vision lies in how it turns complexity into clarity. Gravity, time, light, and motion are not separate things, but different faces of one continuous reality, space-time. There's a certain peace in that. The universe doesn't need hidden forces or invisible threads to hold itself together. It just follows its own geometry, letting every object, every ray, every ripple move along the paths that shape demands. Even chaos, when seen from far enough away, becomes graceful. Galaxies collide, stars explode, planets spiral in and out of orbits, and yet the underlying harmony remains. Each motion is part of a deeper order, written into the structure of reality. From the fall of an apple to the merging of black holes, everything follows the same quiet rule: move straight ahead through curved space and time. That single idea unites the everyday with the cosmic. You, sitting here, are bound by the same geometry as the stars. Your heartbeat measures time just as the pulses of a distant pulsar do. The ground beneath your feet curves space just as Jupiter does, only more softly. The same equations describe it all, from the faint gravity that holds your cup on the table to the colossal gravity that binds galaxies together. It's humbling to think that the very same curvature that keeps your feet on the ground also governs the birth of stars and the life cycles of worlds. Einstein's insights stitched every scale of existence into one coherent fabric, and within that fabric, everything moves, not by command, but by consent, quietly, inevitably, beautifully. The geometry of space-time is not static. It evolves as the universe does. Mass moves, energy shifts, and the fabric flexes in response. The cosmos, in its endless patience, is always rewriting its own shape. When stars die and black holes form, the local curvature deepens. When galaxies drift apart under cosmic expansion, space-time stretches and cools. Even the empty regions of the universe, the vast voids between clusters of galaxies, are part of this dance, expanding faster and faster under the influence of dark energy. No place is truly still. Every corner of the universe is in motion, part of an ongoing transformation that began with the Big Bang and will continue long after the last. Light fades. Einstein's equations don't just describe this evolution, they allow us to predict it. They show that space itself can expand, that time can slow, that gravity can create and destroy structure. They tell us that the universe has no fixed stage, no rigid backdrop. Everything, even emptiness, is alive with geometry. And that means every story written in the stars is also a story of space and time reshaping themselves. The galaxies you see when you look through a telescope aren't where they appear to be. Their light left them millions or billions of years ago, traveling along curves that have shifted ever since. By the time it reaches your eyes, the universe has grown larger. The distances longer, the geometry subtly changed. What you're seeing is both now and then, a layered echo of space-time's memory. Every photon is a message from the past, and every gravitational wave, a whisper from a deeper moment of creation. The cosmos, vast as it is, holds all of these in a single continuum, like ripples frozen in slow motion. And through it all, one truth remains. Gravity is not a force pressing down upon us. It's the shape of the world we live in, the gentle bending of time and space that cradles every movement, every orbit, every heartbeat. We're not standing on the surface of gravity. We're immersed in it, woven through it, drifting within its calm, invisible curves. The next time you look up at the night sky, take a slow breath and remember that you are not just looking out into space. You are looking through space-time itself, through the living geometry that holds galaxies, light and life in its embrace. And somewhere, far beyond the reach of light, the universe is still humming softly to itself. The hum of the universe is faint but endless. It's the quiet resonance of space expanding, of stars being born and dying, of black holes merging in the dark. If you could somehow listen closely enough, you would hear that song everywhere, not as sound through air, but as the shifting of space-time itself. The subtle rhythm that shapes all things. We live within that rhythm. Every breath you take, every orbit of the moon, every flicker of starlight is part of that same ongoing melody. Time, gravity, and motion are not separate instruments. They play together, forming the harmony that holds the cosmos together. Einstein's great gift was showing that this harmony isn't an illusion or a metaphor. It's real, measurable, and astonishingly precise. He showed that space and time form one continuous fabric, that mass and energy bend that fabric, and that the bending tells everything else how to move. From those few simple principles flow every effect. We've explored time dilation, gravitational redshift, the bending of light, the precession of orbits, and the ripples that carry across the cosmos. It all fits together with quiet inevitability, like notes in a song that never ends. Even the way the universe grows obeys this geometry. Space itself is stretching, not into something, but of itself. Galaxies drift apart not because they're flying through empty space, but because the space between them is expanding. This expansion doesn't pull them apart like a wind. It carries them as part of its flow. The same curved geometry that explains falling apples and bending starlight also describes the fate of everything from clusters of galaxies to the entire observable universe. When we look back in time, we see that expansion leading to an origin, a moment when space, time, and matter were all compressed into a state of pure energy. The Big Bang. It wasn't an explosion in space. It was the expansion of space itself from an unimaginably dense beginning. Since then, the universe has been cooling, stretching, and evolving. Stars formed, galaxies assembled, and over billions of years, matter gathered into the intricate web we now see. Each of those structures, every spiral galaxy, every shining nebula, is a manifestation of geometry in motion. The same equations that describe how a ball falls to Earth also describe how galaxies, clustered together under the gentle pull of cosmic curvature. We are part of that same story. The atoms in your body were forged in the hearts of stars, carried outward by supernova explosions, scattered through space, and later drawn together by gravity to form planets, oceans, and life. You are quite literally made of stardust, assembled by space-time's own design. Every breath you take is filled with particles that have traveled across billions of years, guided by the shape of the cosmos itself. And so, when you gaze upward at night, you are not separate from what you see. You are made of the same fabric that carries the light of those distant stars. You are space-time looking back upon itself. That's perhaps the most beautiful consequence of Einstein's discovery. It doesn't just explain the universe, it connects us to it. It tells us that everything, from the smallest grain of dust to the grandest galaxy, exists within one continuous whole. The boundaries between here and there, between past and future, between being and falling, all dissolve into the same geometry. The universe is not a stage we walk upon, but a living fabric that includes us completely. In a way, we are all falling together, planets, people, photons, galaxies, each following the same elegant rule written into the shape of existence, falling freely, effortlessly, in the curved embrace of space-time. There's peace in understanding that. It means that motion and stillness, gravity and weightlessness, time and distance, all are different expressions of the same quiet truth. Einstein's equations are at their heart a love letter to symmetry. They describe a universe that balances itself perfectly, where matter shapes geometry and geometry shapes matter. It's a partnership that needs no overseer, no external push. Everything simply is as the shape of space and time allows. And that shape, though it may bend and ripple, holds together with exquisite consistency. Even now, scientists continue to test Einstein's vision with ever greater precision, watching pulsars spin, tracking spacecraft around planets, timing the arrival of distant signals. Each test, each observation, returns the same verdict. The fabric of space-time behaves exactly as he said it would. The closer we look, the more perfectly the universe keeps its promise. There may still be mysteries beyond quantum gravity, dark matter, dark energy, hints that space-time has deeper layers yet to reveal. But whatever comes next, the foundation Einstein built remains solid serene, and profoundly human. He once said that the most incomprehensible thing about the universe is that it is comprehensible. Somehow, our minds, small and fragile though they are, can glimpse the grand design of the cosmos and see the order behind the mystery. Perhaps that's what makes the universe so quietly comforting. Beneath all the vastness and distance, there's coherence, a rhythm, a structure we can understand. And when you lie awake at night, listening to the world's hush, you can remember that you are part of that same calm geometry. The ground beneath you is curved, the air around you follows those curves, and the light that touches your eyes has journeyed through space-time's graceful contours to reach you. You are not apart from gravity, you are within it, moving along your own geodesic, part of the same cosmic story as every star. The next time you feel small under the stars, know this: the stars are not above you. They are around you, within you, and made of the same space-time that shapes your heartbeat and your breath. In the end, gravity isn't what keeps you grounded. It's what connects you to the planet, to the stars, to everything that has ever been and ever will be. The universe is vast, but it is also intimate, woven together in curves that hold us all. And in that gentle curvature, in the patient hum of space-time, there is peace. So rest now, and let that thought carry you into stillness. The same geometry that guides the galaxies is watching over you too. This idea, called emergent space-time, turns everything upside down. It suggests that space and time themselves might not be the deepest ingredients of reality. Instead, they could arise from something even more fundamental: a network of relationships, information, or quantum entanglement. In Einstein's view, space-time was a smooth, continuous fabric that could bend and stretch. But as physicists began probing smaller and smaller scales, approaching the Planck length, about 10 meters, that smoothness began to blur. Quantum mechanics, the theory that governs the tiniest particles, refuses to let anything stay perfectly still or precisely defined at those scales. Space-time itself may fluctuate, bubbling with quantum uncertainty like foam at the edge of the sea. The very geometry that seems so solid on human scales may be woven from countless invisible threads of information. If that's true, then space-time as we know it is an emergent phenomenon, like temperature arising from molecules in motion, or sound emerging from vibrating air. No single molecule has temperature, and no individual vibration has music. Those are properties that appear only when countless pieces work together. In the same way, space and time may appear only when vast numbers of quantum bits, qubits, interact in particular ways. This vision is still young, still forming, but it's deeply compelling. It suggests that the geometry we experience, the curvature, the gravity, the flow of time, is a kind of large-scale illusion. A pattern arising from deeper rules we can't yet see directly in this picture. Gravity itself could be a side effect of quantum entanglement, the strange bond that links particles even when they're far apart. Entangled particles share information instantly, as though they're connected through invisible threads that ignore distance. Physicists like Juan Maldacena and Mark van Romstank have proposed that those threads may literally be the threads of space-time. That entanglement weaves the universe together. In this view, space is not fundamental. It's built from connections. The more two regions of the universe are entangled, the closer they appear. Break those entanglements, and space itself begins to fall apart. It's an astonishing idea. Geometry arising from information. Distance is defined not by meters but by the strength of relationships between quantum states. The cosmos as a web of correlations, with space-time as the tapestry those correlations create. One of the most striking versions of this concept is the holographic principle. It proposes that everything that happens in a volume of space can be fully described by information stored on its boundary like a hologram, where a two-dimensional surface encodes a three-dimensional image. In a sense, our universe could be a projection, not unreal, but emergent, like a reflection cast from a deeper layer of information. The inside of a black hole seems to follow this rule. Its information, the record of everything that has fallen in, is stored on the event horizon. A two-dimensional surface. The holographic principle extends that logic outward, hinting that the entire universe might work the same way. Space and time, and everything that happens within them, could be the unfolding of information written on a cosmic boundary we can't directly see. It's an idea so bold that even Einstein, with all his imagination, might have paused. Yet it fits beautifully with the mathematics of relativity and quantum theory. It could resolve the deepest puzzles about black holes, how information survives when matter falls inside, and why space-time appears so smooth when quantum theory says it should be grainy. If space-time is emergent, then gravity isn't fundamental either. It's a large-scale effect, like pressure or temperature, a collective behavior of countless microscopic ingredients. We feel its smooth pull because we're too large, too slow, to see the quantum granularity beneath it. The equations of general relativity would then be like the equations of fluid dynamics, a description of the average behavior, not the underlying machinery. Somewhere below that smooth surface lies a realm where geometry dissolves into pure information, and space and time are no longer meaningful at that level. Reality may be a vast sea of quantum connections, a pattern of entanglement and uncertainty. When enough of those connections form in the right way, space-time crystallizes out, like frost forming on a window pane. Geometry condenses from information. Time begins to flow. This idea bridges two of the greatest theories in science, general relativity and quantum mechanics. Each describes a different side of nature, one elegant and continuous, the other probabilistic and discrete. For a century, they've resisted unification. But emergent space-time may finally offer a path between them. If the universe truly arises from information, then everything from gravity to consciousness may be expressions of the same underlying code. Physics, in that sense, would not just describe the universe. It would describe the way the universe computes itself already. Researchers are exploring this frontier through thought experiments and mathematical models. In certain simplified universes, known as ad spaces, they've shown that every feature of gravity can indeed emerge from a web of quantum entanglement on the boundary. It's as though the shape of the universe is drawn from the pattern of its own connections. Perhaps our cosmos, vast, expanding, and filled with galaxies, works in a similar way. The geometry we inhabit could be the visible shadow of invisible quantum relationships. What this means for our understanding of reality is profound. If space and time are not fundamental, then asking where or when something happens may not be the deepest question. The truer question might be how the information is arranged, how the relationships between the smallest bits of existence give rise to everything we perceive. In that view, even consciousness could be part of the same emergent order, awareness arising from the flow of information within space-time, just as space-time arises from the deeper web beneath. It's a humbling thought, but also a hopeful one. It means the universe is not a cold mechanism, but a living network, interconnected, and endlessly creative. The same geometry that bends around stars might one day be understood as the large-scale echo of something far simpler and far more beautiful: information in motion. And if that's true, then the story of physics is far from over. We've traced gravity from Newton's pull to Einstein's curves, from ripples in space-time to the quantum threads that may weave it all together. Each layer reveals not contradiction, but continuity, a deeper harmony hidden beneath the surface. Perhaps, in the end, there is no final theory, only ever-deepening understanding. Each step closer to the truth changes what truth itself means, showing us that the universe is not a puzzle to be solved, but a song to be heard. One note, one discovery at a time. And maybe that's the quiet lesson of all of it, that reality, for all its complexity, remains calm at its core. The same calm you feel when you lie under the stars, listening to the hum of the night, is the calm that underlies space-time itself. So, as you drift towards sleep, remember that you are not separate from that hum. You are part of it, a ripple in the same geometry, a note in the same cosmic song. Good night, traveler of space-time. Rest well in the curve of the cosmos.